I'm going to talk to you today about something that I've been working for about 11 years. It's a lot. I actually realized that when I was putting these presentations together. And you have to wonder, I've actually done a lot of other things as well, but I still feel as passionate about it as when I first was exposed to this topic. So hopefully at the end you will see why. So what I want to talk about a little bit here is some ground truths, right? We all know, and you've probably seen a lot of surveys, you've seen from different reports that the wireless usage is just going up tremendously. And then also the amount of data that the users are consuming is going up tremendously as more and more of the smartphones proliferate, tablets, Wi-Fi, LTE, ubiquitous connectivity, it's just going up. Now, in our labs, we have a whole lot of applications and things that we are building. And as I look at them, the demand, the requirement for bandwidth is just going to go up with all these applications. And although the mass public hasn't seen those, but I have, and I know they're very addictive because once you get used to it, you want them everywhere. It's not going to be enough to do them in desktop as well. Now, when you say, you hear people talk about LTE, it's great. You get lots of bandwidth there, no problems. But the latency is the killer. The latency is pretty large, and I don't know how they will solve, or this in the cellular domain will solve the latency problem. So generally, what is happening is that more and more demand for connectivity, but if you sort of project further, you sort of see that this is a problem because not only do we need to connect people, but we also need to get them the services that they most care about, and not the current generation. So if you look at spectrum, which is what is needed for wireless connectivity, and you look across the world, people have taken the spectrum, which is a very important national resource, and partitioned it and allocated it for different uses. You see the FCC chart for the United States, and then you see for other countries. And this is true for country after country. It's the same sort of thing. You take the spectrum and you allocate it. Now, so what can we do? Given that we need spectrum, what can we do? Well, we can fatten the pipes. That means find some additional spectrum. But as I've already shown you, most of it is allocated. So where the heck do you find it? The other thing is you extract greater juice out of it. That means more bits per hertz. Now, we know that we are actually doing quite well already on that regard. I mean, turbo codes, for example, get you pretty much to the limit of what you can get from a certain amount of hertz. And Shannon theory tells us how much we can actually get. And the really key there is thermal noise, and there's nothing you can do beyond that. I mean, that's just physics. So you can't really extract more out of that. So another idea is to change, excuse me, do more spatial reuse. So if you're familiar with wireless networking, you make the cell size smaller, and as you make the cell size smaller, you can increase the capacity. Of course, that comes with some management headaches, and you have to do a lot of the handoffs you have to manage, and you have to sort of have a lot more equipment out there, et cetera, et cetera. But that is the direction that a lot of the cellular folks have been taking, which is the small cell, or previously called femtocells, in fact, both. And then another idea is to sort of say, well, there's a whole lot of spectrum. Some of it is not being used, and if company A owns it, why doesn't they sort of sell it or lease it out to somebody else? So that means you create secondary markets out of it. And a final idea could be that you promote what is called dynamic spectrum access, and that's where most of my talk is going to be about. So these are sort of the framework within which you can work, given that the demand is going up and what you need. All right. So I started this in 2011, and it's true, in 2003, I had my first exposure to the complexity around wireless and spectrum. And I had actually been doing wireless research for a while before I got to that point, but I never really thought about it from a global perspective, a national perspective. It's true, everyone wants more of it. That was clear. And the question at the time was, well, even if you get it, what's the right thing to do? Should we sell it and make it licensed, or we just provide unlicensed? And there were good arguments on both sides. People, even to this day, argue about that a lot. They talk about Wi-Fi and see how successful it is, and then somebody will come and talk about the cellular guys and how successful they have been. And so there are pros and cons to all this. I also got exposed to this gentleman, exposed to his work at that time. I don't know how many of you know about him. It's okay if you don't, because even the people in the know who have been working in this field for a long, long time don't know about him, which is surprising. But he is a Nobel laureate, and he was the first person to sort of talk about the allocation strategies for spectrum. And he made it a point to say how bad FCC and other regulatory bodies had gone out and how they had given this out, a national resource. So it was a really good piece of work, of course. And during that time, Stanford University organized this this event where I really wanted to go. There were all these people there. I don't know, some of you may or may not know them, but they are considered the thought leaders in this space. And they were a mixture of lawyers, a mix of policy advocates, a mix of engineers and researchers and all kinds. And I wanted to be there. And if you want to be in a place like that, you should bring something to the table. So what I did at that time is I actually wrote this paper, and I presented it to the workshop, and they wanted to know what I meant. So the idea at that time was, well, people should have good spectrum etiquette. Meaning do the right thing, that sort of thing. So they wanted to hear, but it was very clear that that's not the way the world works. I mean, one person has the etiquette, doesn't have, the other person doesn't have, there's no enforcement going on, it doesn't really work. But that's okay. It made me think very hard about what does it even mean to have spectrum etiquette, and it got me a seat on the table. Now, this was also the time when people started to sort of talk about dynamic spectrum access. And the idea was sort of gaining heat, and people think, this may be the way out. So what is dynamic spectrum access? So if you sort of look at the left, I guess, my right, your left graph, what it says is that this is a small experiment that an intern of mine did to see that, as you look at the spectrum across the world, you sort of, or across the region, you sort of see holes in it, that it's not being used. And so the question then is that if there are holes and the spectrum is not being used and I really need it, why don't I use it? Okay, so then the question is, well, you can't really use it because somebody else owns it. So there's a primary user for it. So then people say, well, okay, so what if we could come up with a technology which would sense a primary user, and if the primary user is not there, it'll use it. That's the green client there. And at the moment the primary user shows up, it just moves to the next place that is available. So theoretically, conceptually, it is very pleasing. And so can we actually build a technology like that? That became the thing. So then, if you really think, if you try to fantasize, and that tells you why it's been 11 years that I've been working, and I suspect I'll continue working on something like this for a long time, you would say that the way the FCC has partitioned the spectrum is all wrong. It should all be dynamic. And then you should allow some people to be primary users, and some can be secondary. Okay, in that case, then you would have the technology to say, when the primary user wants to use the spectrum for wireless communication, that's, that user gets the priority. If not, then the secondary user can use it. And if you could build it, then you would have no spectrum problem. You would have no wireless communication problem from that perspective. You could build all kinds of technologies, and you will be golden for a long, long time. Pretty much, this is the best you could ever do. But of course, this is not going to happen, at least I suspect not in my lifetime, but it's good food for thought. It's good intellectual exercise to do. Now, during this time, another interesting event was happening. In 1996, Congress had set the transition of digital TV to analog TV to digital TV. And the rule of thumb generally is that as you move that, you use 3 times less, or you use 1/3 the bandwidth that you would have used for analog. Digital uses 1/3 the bandwidth of analog. So now, all the places where broadcast TV existed that was going to become empty. A lot of this, the spectrum was going to become empty. So that was really exciting. And of course, everybody said, I want that. Okay, so then these white spaces are the gaps. So what I want you to do is, this is just a slice of the spectrum, and if you sort of look at that, focus on the yellows and the reds. So when these things were going to be freed, and actually they have been freed because this was in 2009, the red one was sold off to AT&T and Verizon and the telcos, and the yellow one was left open for potential unlicensed use. Now this was amazing spectrum because if you think about Wi-Fi, it works at 2.4 gigahertz or it works in 5 gigahertz. But this one was close to 700, 500, 800, around that area. And the propagation properties of radio waves on those frequencies is much, much better, right? They just go much, much farther. They can penetrate through walls. They can, I mean, think of it, if you want to think of the TV. I mean, for those of you who saw TV with antennas, you know, that can pick up signals even when the base station is very, very far away. So this was great spectrum. So it had long range, and if it was unlicensed, and deep penetration. So as a reality check, we actually did some experiments as well. And here's a little thing that I did many, many years ago. This is the Redmond Campus, and the white thing there, white lines show the shuttle moving around with a receiver. And on your left side is the graph which shows signal strength. The idea of showing the signal strength is that when the signal to noise ratio is over a certain limit, the receiver is able to decode it. Okay, so this tells me by measuring the signal strength, I can say up to what point I can decode and have connectivity. And what we discovered with unoptimal radio receivers, and also with not going at the highest power level that is now allowed, we could get pretty good range. Okay, so we can get like about 1.6 kilometers or 1 mile. Okay, easily, not too bad. So then if you do the math again, you say that all of Redmond Campus, which is pretty large, Microsoft, the entire campus could be covered by 4 or 5 base stations. And you would have complete connectivity no matter where you went, inside the building, outside the building, everywhere. And that was cool. The other thing is that other set of experiments we did was about penetration, which I talked about. And of course, we found that, I don't know if you have houses in places where, like for example, the way my house is constructed, at some points I don't get Wi-Fi coverage at all. And so something like white spaces or UHF will provide coverage everywhere in the house. So you can do more multimedia, more interesting things inside the house too. So then the technical question is, how do we know that the spectrum is available for us to use? Right? Because that's the whole thing about dynamic spectrum access. You sense it. If it's free, you use it. If it's not, if you're the primary user, you go away. Well, you sense the channel. As I said that. But it turned out that even after many, many years of work, we could not do it all the time, 100%. Accurate. Now imagine that if you're a primary user who's paid for it, and I have a sensing device which kind of does it most of the time, but every once in a while it screws up and it does not able to detect it properly, and I start transmitting, and you have to suffer the consequence of that, you're not going to like that. So you can't put technology in the field which is not 100% robust. So while advocates of sensing, including me to some extent, were very, very excited about it, we were not ready. Technology was just not there yet. Okay, so is there another way to do this? Well, we wrote this paper a while ago. This paper was actually written after the fact, and the answer is that there is another way, and that is if some authoritative source tells me that there's spectrum, empty spectrum, and I can rely on that source, then great. Then my problem is solved. I don't have to sense it. I just got that information, and it's accurate because I got it from a source that I trust. So that is what is called the white space database, okay, that you may have heard in the press all over the place. So there are devices, in this particular case, when devices will only use the channels that the white space database says is available to them. Okay. The second rule you would say is that devices will go regularly to check if that channel is still available. Because it's not like you go there at some point and you use it and you have it forever. You don't, because those, like I said, they're the primary channels and they can be used by others. So you have to go regularly and check it. Now, as a database provider, you have to make sure that everything you're saying is legit. It has to be accurate, and you cannot screw up with the primary users. And then you can also say, well, this is a very powerful means now, because now I can pretty much control what channels a client uses, because even if a channel is free and it's used by somebody and that suddenly has become a primary user now, then I just block it. Okay, so it's a very powerful centralized thing. So this is sort of pictorially what I just said. You've got the FCC database, which knows about who's using what in what spectrum. And so all that database stuff goes into what these companies now that you've heard about, which provide whitespace spectrum and whitespace databases, they provide. And then all the clients or the base stations that operate will go and consult these whitespace database, get the answer, and then based on the channel that is available, they will connect. Okay. So we also, of course, we were a big advocate of this, and this was during the time when none of the rules were made. So we built this thing. We built a database, and what I show you is an old version of a database that we built. Okay, so for historical reasons, this is a good picture, but newer are better. So what you're seeing here is on your right sides are reds and yellows on the channels. The red says those channels are not available. The yellows or the whites say these channels are available. Okay. And then down there that you can't really see very well are the details, are much more heavier details about who is using what channel, where, with how much power, and where all, what is the propagation property, etc., etc. You can click on those things and get a lot more detail. So that's not the most important thing. And we're actually pretty proud of what we built. I believe, I haven't checked the latest and the greatest databases that are out there, but I believe that ours is still one of the best, was the best at the time we produced it, and still is. And the reason I say that, make that assertion, is primarily because of this right graph here. So what we did is obviously we took all the database entries from the FCC, then we took all these terrain models from that NASA had and other places had. And to that, we applied some very sophisticated propagation modeling shown by these equations on top. I mean, it doesn't really matter. And then we then checked whether what we were predicting. And what we were predicting was that if a channel was occupied in a particular place, so if there's a base station in location A, up to how far is that area not usable? And you can only do that through propagation modeling, right? I mean, otherwise, how would you know up to what point this is valid and it's not valid? And that's why you needed all this sophistication. You needed a terrain model because radio waves propagate differently. You needed a much more sophisticated propagation model to sort of give you the ground truth. And what you see on the left top is 1,000 places where our student interns went and measured the data and compared it to what the theory was predicting, and we found it to be great. And what the graph here on your left bottom is showing is a CDF, it's cumulative distribution function, which essentially means, and the way to think about it is that right is bad, left is bad and right is good. And so the left part, the green, is when you just assume free space loss as the simplest propagation model. And then on the rightmost, you see the blue line, which is the more interesting models that we have used with the terrain. And it says that you're not, if you use something simple like free space, you're going to lose a lot of space where you could have operated your wireless devices, and it's no good. So you really want something that is as accurate as possible. And we had that. Okay. So now, the other question is, and some of you who in the know would say that, hey, but are there enough channels available to us? And the answer is yes, they are. This is, at least this was done a while ago, but nevertheless, you see that these are the number of channels. And then if you do just some arbitrary but reasonable bits per second per hertz calculation, you get how much bandwidth is available to you if all this thing works really well. And this is for some of the suburban places and some towns like Bellevue and Redmond. But also, you see New York, and LA is not here, but you start to see that they don't have as much, and for various reasons. So there's an argument there that perhaps in the very dense setting, this may or may not be as useful as it may be in the rest of the country. All right, so then we built the whole thing, right? So we were trying to convince at the time the FCC to make this happen. And that's why I use the term first that we built, because this was the first instantiation of Wi-Fi, wireless white space network anywhere in the world. So what we built is we built a white space network. We put some antennas on building 112, which is here, and then we took a shuttle, campus shuttle that takes people around, and in there we put a white space device. And the idea was, as the shuttle moves around, people who sat in the shuttle would connect to our device through Wi-Fi, and that device would then connect through white spaces into the building and then to CorpNet. So as the shuttle moved around, they had full connectivity, and they didn't have to pay any price to cell towers, and it was huge bandwidth, low latency. It was like being connected to Wi-Fi, right? And you could do everything that you did all over the place. So, and this was a really successful experiment for us. So I'm going to show you a little bit of video of what I've said to make it concrete. So let's play this video, please.
With the ongoing transition from analog to digital TV, more and more spectrum is opening up. Adaptive radio technologies allow networks to have the advantages of inexpensive Wi-Fi and the long range of cellular. These technologies can help us use that spectrum by dynamically finding and using the white spaces between frequencies used by existing broadcasters and wireless microphones. This allows more users to coexist on the spectrum. Microsoft researchers have been exploring this challenge for many years and have created a network that finds and uses these white spaces. This technology uses your location and information from nearby transmitters to determine what frequencies are available, then dynamically moves to the frequencies for use in those white spaces. Technology like this can offer low-cost connectivity for underserved communities, schools, or hospitals. By ensuring that this spectrum is available for unlicensed use around the world, government policymakers can help innovators find even more uses for this bandwidth and preserve the economic and social value of this important resource.
Okay, so this sort of reiterated some of the things that I said. This is an old video. I'll show you another one, which is sort of new later. So then the FCC chairman at the time visited us. It was a Saturday. He came with his chief of staff, and we showed him the whole thing. I personally gave a 2-hour talk to him in a small conference room, just with like 4 or 5 of us, and he had lots and lots of questions, and interesting, good questions. But and we showed him how everything worked and how the interference it would not interfere with the incumbents and all that other stuff. Now, I believe actually that discussion was monumental in terms of turning his mind, because while everybody was talking about this stuff, nobody really built it up. Nobody had actually proved that this thing works, and here it was, for the taking, and everybody could see that the thing works. And so then the FCC, a month later, after he came, there was a vote, and unanimously they approved that they wanted to open up the spectrum for unlicensed use, which is what we were going after. So it was a big, big success for us, and we had parties and all that good stuff to say that we had reached our objective. Now, so what did we achieve, right? So if you sort of look at this graph, on the horizontal axis is range, okay, on the vertical axis is speed. And if I took a sort of a coarse view of things and sort of drew some pictures, this is what we had in the unlicensed space. This is where we were operating. Now, because of this this sort of accomplishment, we had achieved this, right? We had a lot. We didn't have as much bandwidth potentially because of the way the frequencies are arranged. It's like you had channelization of 6 megahertz, etc. But you had a lot better range, and so now you can start to think, what can I do with this thing now that I have? Is it really super Wi-Fi? I mean, is it really? Can I achieve everything that Wi-Fi achieved plus more because now I have this range and good property? So there was a whole lot of business opportunities here, right? One is create a whole campus network, which is what the subject of this real talk is right now. Which is in Microsoft, for example, you of course have connectivity here in the buildings, but as you go between buildings, you will have full connectivity. And then you can think about citywide. If you remember, people tried that with Wi-Fi meshes, and we tried it as well. But now there was a reason the penetrations was not that good, but now you can achieve that. What about really big giant hotspots? right? Somebody puts it up, and you can connect from a kilometer away, a kilometer, 1.6 kilometer, or a mile away, or something. What about the idea that Walmarts of the world, or Sam's, or whatever, Costco, etc., put up these big giant base stations on top, and then everybody around them have connectivity, and you can start to see free things coming on their thing. Wireless multimedia. I mean, there are lots and lots of these things. I just picked a few, which I thought would talk about the different things that it is able to do. Now, this was so successful for us that that a lot of regulators from all over the world visited us to see this thing working. And they had a lot of questions with us because they too were obviously suffering from the same issues that the US is, but they were just a little bit behind. And so we showed this to a lot of them and started to have influence on their thinking of how they're going to think about their national resource, which is the spectrum. We also got a couple of PhD theses out of it, some of the students who work with us. Now, since then, we've done a lot more. I haven't actually put slides in to sort of talk about all the different things we have done, but really there are trials going on all over the world. Okay, these are deployments and trials going on all over the world. This is a little picture that shows where they are going on. And the two significant ones of these that I do want to just spend 30 seconds on each is one in Cambridge. This at the time was one of the biggest trials that we did. This was in the United Kingdom, and we were able to work with a lot of vendors, both hardware and database providers, etc. And this was a nice setting because it was both rural and urban, and we had many of the real-world practical issues that we had to be solved were solved in this trial, and this was also a very successful trial. Now, what I didn't emphasize much earlier was that one of the driving reasons for doing a lot of this stuff was actual rural connectivity. This was about people who couldn't afford to pay money, but they still needed connectivity. Microsoft has been a big believer in this. We have spent lots and lots of money and lots of our cycles working on the digital inclusion programs that we had here in the past. So it was just, to us, it was the normal thing to do, which was to think about places that don't have connectivity. So we have an initiative called For Africa. You can go to the webpage and the website and check it out. And in there are multiple trials that have been running by our technology policy group here, which is very, very vocal and very, very sort of aggressively moving the world in this direction. And so we did a pilot in Kenya, and for various reasons, and the government in Kenya was very happy. But I want you to read this quote that I picked up. And this came completely unexpectedly. This is, and I'll just give you 5 seconds or 10 seconds to just read it. So this is from people, we just, here we just assume that connectivity is our birthright. And for the large parts of the world which actually don't have it at all. And the telcos are not willing to go there because that's a lot of money for them to spend, and they're not going to get anything back. But now you have a technology that actually does not require that much money to spend, and yet provides connectivity. So this whole thing about digital inclusion, digital divide, etc., is all about information divide. If you don't have enough information, you're not going to make great decisions. And if you don't make great decisions, you won't be able to improve your economic standing in the community. And so this quote here talks about the student who suddenly his eyes lit up and his world lit up because now he was actually able to experience some of the things you and I experience. So this was a really good thing, and of course, for some of us who work in this field, it was very, very satisfying to see that. So now, in terms of current status, there's, from a policy perspective, in the United States, is the leader in all of this stuff, and we've done a whole lot of work. The UK is not so far behind, and then there's a whole lot of countries that I've listed here where the policy is on various stages, the regulatory policy in terms of deciding how they want to approach this, whether they should do it with databases or not. In terms of standardization, which is really important as well, the right things are happening. The IEEE is pretty heavily engaged. They actually have a standard, I think, that they published recently. And standardization is key. I don't know how many of you have been working in wireless for a long time, but I have. And for example, Wi-Fi came in 1989. I was using that in 1989. But it wasn't until 1997 when the standards were passed and then people started to get mass products out there that it really took off. So it took a long time then. I don't expect it'll take as much time in white spaces, but standardization was the way to get everybody's laptop have this, or everybody's notebook have it, or everybody's smartphone have it. And this is progressing. So as I look at this thing, I see the same set of progression, and so that gives me optimism that we are going to get there as well. And there are other bodies too, Wi-Fi Alliance, which looks at certification and interoperability. There is the IETF, which talks about the standards between the client and the databases, and they are writing it. And then the European standards and the US administration. Now, if you sort of look at database certification, there are several companies which have now been certified by the FCC to have the database and to be able to provide those database services. Today, for example, you can buy a certified device and you can go with a certified database and install this thing without any requirement from FCC on your campus. You can do that today. Okay, so you can have whitespace network on your campus for all your employees today because of all the rules and all the progress. So similarly, there have been many devices that have been certified. Of course, as they build, they get sent to the FCC, and then the FCC says, yep, this is compliant with all our rules, and this is what we expect. So you can now go and sell it. You get the FCC sticker and you buy it. So that is happening. A whole lot of companies are doing that, and you can just check that out in the thing. So here's another video. This is actually a little bit of a repeat of that video of what I showed you. But it's a little bit more emotional, I think, and it makes a point, and I'll show you the point. So let's roll this one, please.
What if you could better educate children living in a remote village who lack access to specialized instruction? What if you could manage traffic so gridlock doesn't stop your city during rush hour? What if you could provide state-of-the-art high-tech medical care to people living in remote communities? What if governments could use technology to better deploy city services, such as garbage removal, and reduce costs in the process? What if a boy who dreams of playing in the Premier Leagues could finally stream his favorite team's games? If you look for the answers, you won't find them in what's out there. But you might find them in what's not there. It's called whitespace, and it's a renewable natural resource found in unused radio frequencies. These unused whitespace frequencies can be used to increase available bandwidth, improving the quality of broadband connectivity. And lots of these unused frequencies are located between TV channels. Signals sent out on these unused TV frequencies travel far and penetrate trees, walls, and other solid objects, inexpensively extending the reach of Wi-Fi and other wireless broadband technologies currently limited to using higher frequencies. What can TV whitespaces enable? You can manage traffic in your city minute to minute, adapting the infrastructure to accommodate conditions. You can more efficiently deliver public services. You can have medical resources be available for preventive care. By reducing the cost of broadband connectivity, a school can now become part of the global village. The only thing stopping this from happening is the lack of favorable, consistent regulations allowing whitespace technology to be deployed on an unlicensed or license-exempt basis. People and the devices they use will finally be better connected by tapping into the TV whitespace available in your country.
So the reason I wanted to show this video, even after I showed the previous one, was because this had a little bit more on the different scenarios. And of course, the biggest point of this video, which we use, is to put pressure on regulators around the world to come up with regulation that is in harmony with each other. Because if you're building product, it's really hard. If people all agree on it, but they come up with different rules everywhere, then you get screwed, because you can't really build it. We live in one world and we use the same product everywhere, and we want to get to that point. And so this was sort of, to sort of appeal, and of course there's technical reasons behind all this stuff, but I wanted to show that's kind of where we are struggling now, is to make believers out of the rest of the world, and many of the countries are coming along, but that's where we are. So in general, where we headed, logically it sort of makes sense, right? There was an R&D effort which we worked on quite a bit. We proved, we built a prototype, then we sort of talked to the regulators. They sort of moved forward with the regulation. They have done their thing, and now we're doing it all across the world. There are some commercial pilots which I showed you around. There's some pilots I'm showing you that I showed you, and there are other companies which also have their own pilots, and then eventually get to the customer deployment. So everything is progressing as planned. Everything is, and so one of the reasons why we decided to give a talk here was to sort of, as you think about your companies and the places that you work in, you must start thinking and incorporating some of these ideas into this, because the train is moving, and it's moving pretty good at this point. So now, very quickly, I'll end with this thing called the Project Istanbul, which is, so historically, I wanted to say that after we had achieved what say we now is an MSR, we had achieved this objective of getting the FCC to do the right thing. We kind of moved on. We started doing other things as well. And so a couple of years passed, and we actually did not make any progress because we were doing other projects and looking at other things too. But 2 years later, for some reason, sort of came back and looked at this again as to what had happened in the past, and we sort of decided that there were still some hard technical problems that we needed to solve. Okay, and in fact, I was quite bitten from my earlier days when I was also pushing wireless mesh, where we had gone there and done a lot of work, and then the world actually picked it up, and there was a lot of VC funding, etc. But we hadn't yet solved all the technical issues, and I think that caused the problem. So we wanted to go back, and we wanted to build what I called as a researcher's playground right here on campus, but it would have to be a production class network, not a toy network. So the objective of Project Istanbul was to build a campus-wide whitespace network that was on all the time, right? 24/7, 365, and that users were using all the time. So the things we decided was, let's do physical security and put cameras in places, because it's a big campus and people move around at day and night, to make sure that we can get these live feeds. And we can't do it over LTE, it's too much bandwidth, and we can't really do it over Wi-Fi, because these are the areas that we are not going to be there. So let's use white spaces. That was a good example of using white spaces. We also had this idea of digital displays, and we are also playing with small cells, and sort of wanted to see how can we create a backhaul network. Another objective for us was that we were going to do everything in software. Everything would be Microsoft homegrown. So hardware, software, everything. So we have in MSR Beijing, we have some world-class researchers who have done some amazing work with software-defined radios. But at the time, they had been focusing on Wi-Fi, and they actually built the first software-defined radio which interoperated with commercial Wi-Fi. So working with them, we decided that we wanted to move this into white spaces, and we did. But it wouldn't be fun if it was just ours, so we also looked at some of the other universities, and Rice has another software-defined radio framework called WARP. And we also then use a commercial one, which is certified, to see if we can interoperate with all this stuff. So this picture didn't come out very well. It's kind of grainy, but what we did is remember I told you earlier that our thought was that 4 or 5 base stations could cover the entire campus. So we have installed 4 base stations in 4 different buildings on campus. And the idea is now that once installed, you can have mobile units moving around that can connect to them, which could be this, and you can have all these hard-to-reach places, have units that are connected to these base stations, and then offer Wi-Fi coverage there, so long as we still have Wi-Fi and we don't yet have the dongles for white spaces. In terms of the SORA, so I already mentioned this. This is just a pretty picture showing that you had the software radio, and then we had to change the front end of it to operate at the lower frequency bands, because as I said, they had initially done this for Wi-Fi. So we created that. That's an antenna sitting there. That's on the top is the actual SORA board. Now this is pretty large, and that's okay. This is research. We want flexibility. And because of the requirement of that flexibility, we don't necessarily at this point care so much about form factors. But there is no fundamental reason why it can't be as small as what you have today with Wi-Fi, right? So don't let these pictures bother you from that perspective. The second one is the RICE board, which is the warp board, which we are using in interoperating. And the third is the Adaptrum board that I talked about, which is the commercial board. This is also pretty large at this point. And then, I mean, we didn't hire anybody. We ourselves had students. There's a little picture of going in, installing an antenna. You see a little box there with the Sora board in there. And then you see a building, which is Building 99, which is my building, which is where I work. And the corner of that, there's where the antennas are. And here again, some more pictures again of Clay, who's a fifth-year PhD student at Rice, installing all this stuff. And there's a lot of antennas there, so there's no reason to be sort of worried about so many antennas. We are just testing a whole lot of things with all these different antennas. We want to do MIMO, we want to do directionality, and all that kind of stuff. So it's a little overkill for a real use, but we wanted that flexibility. Here's a pole top receiver. This is in a soccer. We have a commons area where there's a soccer field, and we placed a receiver there. On your left top is the bottom of that. There's a little camera there which is pointing towards the soccer field, and then on your left bottom is a receiver with the solar panel. So we actually have on Building 92 a receiver which is completely charged by solar energy, and there's no even electricity there. So this is like the most beautiful thing you can have, with no wires, no nothing. It just works and provides connectivity. Here's a little picture of a client. It's a little box right now, and it's mobile. It's got a battery in it. You can move it around, and it connects. Once again, like I said, this is all much bigger than it needs to be right now. Here's a little demo we did a while ago, which is, you see the box sitting there. There's an antenna, and way out in the corner is this are some of the researchers in a van. This is sort of the highlight of that, and then they're standing, and then they are connected to this thing. And at that time, we needed this large fuel thing to power it because we didn't have the battery. So I'm going to switch to a live shot. So what you have here is, this is not very interesting, but oh, there's some people. Good. So the problem is when I see that, it's like nothing in here. It's so boring. But during the lunchtime, people play soccer and people move around, and that's kind of cool. But what you're seeing here is exactly that pole top receiver that I showed you with a camera underneath, and it's pointing to the soccer field, and you're seeing live video stream from that soccer field right here to all over white spaces. So no wires, no nothing. It's working. So go to the next slide, please. All right, so that's then, and then we move to the next. So I'll just leave you with one bit of research. I sort of said that, oh, there's research to be done. Well, I told you what we've built together, but I didn't tell you the research. So, this is not unlike Wi-Fi. Wi-Fi gets very popular, and then you get, a high density of it. It's called the property, the tragedy of the commons. So what if it happens in the white spaces, right? So now if you sort of deploy this, and this kind of coverage you get, and then if other people build these little white space networks around there, it's going to cause interference. So what happens to your big white space network? It's actually a good problem to have, but it's not a problem which will sort of stop the movement, but it's an intellectually interesting problem to have. So what we've been working on is, instead of beam patterns that look like that, we do beam patterns that look like this. And we believe we can do that. We can do directionality, very tight directionality with multiple antennas. And that's the kind of thing we're working on. And so now if you have this, and you do it in real time, and you adapt very quickly, you should not have the problems that Wi-Fi is having. In fact, we're doing this because this is really, really fun for us, but also a lot of the techniques that we are building here are applicable to all the other wireless technologies as well. Okay, so that's pretty much it. In summary, I would say that the white space technology is actually real. It's real. We've shown it to see we're doing it now. I just showed you a demo, and it all works. Now, there are many scenarios. I did not focus too much on that because everybody has their own favorite scenario that they really care about, so it didn't really make sense. Just showed you some and showed the video on it. we do feel very optimistic that we can get to the point where lots of countries come up with regulations which are very similar to the United States, and then that'll just make the life easier. I showed you that the standardization process is going pretty good, both from IEEE perspective, IETF, and Wi-Fi LANs, etc. Plus, device manufacturers are building it. We've heard that chip manufacturers are building chips. ASICs are coming. And then this continues to be an active area for research, but not of the kind which will make it a bottleneck for adoption. This is the sort of thing that researchers have done with Wi-Fi. Wi-Fi has been very successful, and yet you continue to see innovations through all this alphabet soup of Wi-Fi that you have that keep coming because of all the research that's happening. So that's it. Thank you very much.